Good morning, everybody. Welcome to Tibbetts Physics. What is crappin'? Today we're going to talk about Kirchhoffs laws, specifically Kirchhoff's current law and Kirchhoff's voltage law. So let's talk about Kirchhoff's current law first. And we'll call it KCL. And all Kirchhoff's current law states is that the sum of the currents entering a node or a point is equal to the sum of the currents exiting that node. So it is equal, we'll say, to the sum of the currents exiting that node. So we'll do a quick example. Let's say we have some current entering a node. Let's just call that I1 for now. And that current is going to branch off into 3 separate nodes. We'll call that I2, I3, and I4. And all those currents are going to recombine to another node. So we can say the sum of the currents entering is equal to the sum of the currents that exit. So in this case, I1 is equal to I2 plus I3 plus I4. And we can use this to either solve for one of the missing currents or apply Ohm's law to help us solve for anything else. The other law is Kirchhoff's voltage law. And we'll call that KVL. Kirchhoff's voltage law states that the sum of the voltages within a loop is equal to 0 volts. So what we're going to do is we'll draw a simple series circuit. So we'll have our battery, and we'll add a couple of resistors. We'll make this a 6-volt battery. We'll do an example together. And we'll have a couple of unknown resistors. We'll say that the potential difference across V1 is 2 volts, and V2 is what we want to solve for. Now, what's important for Kirchhoff's voltage law is that we label the positive and negative terminals. So you know the electricity flows out of the positive, enters the negative. And then we also have to label the positive and negatives through the resistors. So positive, negative, positive, negative. If we look at the flow of the charges or the currents, we could say that V1, notice it's positive, plus V2, also going through the positive, then the negative. And watch as we go through the battery, it goes from the minus to the plus. So we can say minus V total is equal to 0 volts. So if we want to find V2, we can just isolate the variable. So V2 is equal to V total minus V1, which gives us 6 volts minus 2 volts, leaving us with V2 is equal to 4 volts. In the previous video, we looked at a combined circuit of both parallel and series, and we analyzed it using a VERP diagram. That was practice problem number 12. We're going to look at the exact same circuit. This is practice problem number 13, except now we'll use Kirchhoff's laws. So if you could copy and paste your circuits on your paper, please, and we'll analyze this together. The first thing we want to do after having our resistors labeled is we want to label our positive and negative terminals. So the left side of the battery is a positive based on the longer line, which means the right side is negative. And we're going to follow the flow of the charges. So the first resistor, positive, negative. If we look at resistor 2, left is positive, right is negative. And resistor 3, the left is positive and the right is negative. So we can now look at the loops that the current flows through. So if we look at our first loop from the battery, it could go through R1, then R3, and back to the battery. And if you look at our branch, it could go through R2, and then around through R3. Notice when it goes through R3, it hits the negative terminal first. What we'll do now is use Kirchhoffs laws to analyze this circuit. The first thing we'll do is look at Kirchhoff's current law. And we could look at the current that flows through resistor 1. We'll call that I1. And that branches off into I2 and I3. So we could say that the current entering a node, I1, is equal to the sum of the currents that exit it, I2 plus I3. The second thing that we know is we could use Kirchhoff's voltage law, or KVL. So if we look at our first loop, we could see that the sum of the potential differences add up to 0. So if we go through V1, notice it goes through the positive then the negative, trace it through, plus V3, minus, as we continue following it to the battery, hits the negative, so minus VT is equal to 0 volts. We can also look at the loop of the parallel resistors, and we see as it goes through V2, and then if we continue that loop, it's minus V3 because it's negative first, and that equals 0 volts. For the third one, we could simplify this and just say that V2 is equal to V3. So from this point forward, we have to use algebra to ultimately determine the current that flows through each resistor. So why don't we look at our second formula, V1 plus V3, and we know V total is 6 volts, so minus 6 volts is equal to 0 volts. Why don't we just add 6 to the other side? So V1 plus V3 is equal to 6 volts. We could use Ohm's law, which says that V equals IR. So we can turn V1 into I1 R1 plus V3, which is I3 times R3. And that equals 6 volts. We could do the same for our third equation. So we can also say that V2 turns into I2 R2 D2, and that equals I3 R3. Notice that our green equation has an I3 in it, and our bottom equation also has an I3 in it. So what we want to do is use some algebra. We know that we can replace I3 R3 with I2 R2. So we're going to go back to our second equation, and we'll write I1 R1 is now, we'll write I1 R1 plus, we could say I2 R2 is equal to 6 volts. Now we also know that from our first equation that I1 is equal to I2 plus I3. So wherever we see an I1, we'll turn that into I2 plus I3. So we have I2 plus I3 times R1 plus I2 R2 is equal to 6 volts. Notice that we have I2s and I3s, so we still can't solve for anything quite yet. But what we do know, or what we can do, is we can solve for I3 from our third equation. So if we isolate I3, we're left with I3 is equal to I2 R2 over R3. So we'll plug that in for I3 in our green equation. So we can say that I2 plus I3, which is I2 R2 D2 over R3 times R1 plus I2 R2, and that equals 6 volts. So from here we know everything except for I2, which means our goal is just to isolate I2, and we could plug and chug. What I'm going to do to help clean this up is just plug in our values that we know. So we have I2 plus I2 times R2 over R3, so that's 5 over 9, times R1, which is 4, plus I2 times R2, which is 5, and that is equal to 6 volts. So let's distribute the 4. So we have 4 times I2 plus 20 times I2, 20 over 9 times I2 plus 5 times I2 equals 6 volts. If we add all these together, we get 101 over 9 times I2 equals 6 volts. And if we solve for I2, we get the current through resistor 2 to be 0.54 amps. Okay, so we got 1 current. Now we got 3 to go. If we look at our equations that we made from above, we know that I3 is equal to I2 times R2 over R3. So we could plug in I2 for that and just solve for I3. So I3 is equal to I2, which is 0.54 amps, times R2, which is 5 ohms, over R3, which is 9 ohms. Plug and chug and we get 0.3 amps to be I3. Okay, and now we know from our first equation that I1 equals I2 plus I3. So all we have to do is add those currents up. Oops. All we have to do is add those currents up from equation 1 to get I1. So I1 is I2, 0.54 amps, plus I3, 0.3 amps, and that gives us I1 to be 0.84 amps. Notice that either way works to solve this scenario, either Kirchhoffs laws or a VERP diagram. It's up to you in terms of which one you're more comfortable with of solving for. Sometimes Kirchhoffs law is easier, especially for a more complicated circuit than this one that we have here. Hope you found this video useful. Please like and subscribe. See ya!